about electric field, they exist around charged particles. And those charged particles are protons and electrons, right? So electrons are negative and protons positive. So electric field lines are going out of positive towards to negative. Okay, so when we go through that quiz, so which of the following is false about electric field lines? Okay, so what is false? That electric field lines are straight lines. So they're curves, right? They can't cross each other. And you have like example here on this picture, so curves. They point out of positive towards to negative, right? And they show how, okay, so this is wrong. How electric field lines are located, like from which fold to which fold. Okay, on this picture, it's more clear. So out of positive, so curved. And if you have two positive charges, so area between them is not affected, really. Okay, so, and the strongest field is close to the charge. So the strongest P field is in point B, so it's close to the charge, positive charge. Okay, for question 3, consider the electric field lines shown in the diagram below. From the diagram, it's apparent that object A is, okay, what is this charge for A and B? So A is negative, so towards to negative, and B is positive. So electric field lines are going out of positive, so out of B, so it means B is positive, and towards to A. So into A, so A is negative charge. Out of positive towards to negative. So combination is negative, positive. Okay, now you have two charge plates, positive on the top, negative on the bottom. Okay, and you see that between two plates, yeah, straight lines. So it's basically density the same, and at the end are curved. Okay, out of plus towards minus. Yeah, so in the middle uniform, in the corner it's a little curved. Okay, based on the arrangement, what are the charges? Okay, so out of positive, right? So both are positive charges, both are the same. Okay, another diagram, which diagram correctly shows electric field around negative charge? Okay, and negative charge takes into, okay, electric field lines are coming into it. Okay, so from positive out, for negative inside. Which diagram correctly shows the field lines between two like charges? Okay, so here it's opposite charges, here like charges. So both are out of, so positive. So both are positive charges, both are like charges. Electric field surrounding positive charge is away. Okay, so it's basically on the same idea, all those questions. So out of positive towards to negative. Coulomb's law. So it's a law between two charges. It's saying that force between two charges is directly proportional to their charges and inversely proportional to square of the distance. So square distance between them. And K is some coefficient in front. So force equal K, Q1 multiplied by Q2 divided by distance between them squared. Okay, so then when distance increases, so distance is in denominator, so force will decrease. That's why like charge, electrical forces and gravitational forces and magnetic forces are related. The further away the object, like distance increases, the less will be the force. Where electric field be found? So in the space surrounding charged object. Okay. So if you don't have charges, there is no electric field there. Then you have also two electrical plates, positive and negative. You have three charges, A, B, C. The magnitude of the force exerted on the charge of electric field between the plates is the same for A, B, and C, because if you remember, density between plates are the same. So uniform field. Okay, so strength is the same between two plates. What is the magnitude of electric field intensity when you have force? So you divide force by charge, and charge for proton is the same as charge for electron. So you divide by 1.6, multiply by 10 in power negative 19, and you will get that number. Okay, so you can use calculator and try. So remember when we have use exponent laws. So when you divide force by charge, so you divide bases by each other. So 2.30 divided by 1.6. And then when you divide powers, 10 in power negative 25 divided by 10 in power negative 19. So negative 25 take away negative 19 is negative 25 plus 19. So negative 6, right? And 2.3 divided by 1.6 will be 1.44. Okay, so straightforward. And 10 in power negative 25 divided by 10 in power negative 19. Negative 25 plus 19 is 10 in power negative 6. So even without calculator, you can see which one is the most appropriate. Yeah, so a little bit more than 1 ratio, and using exponent's laws, you can calculate what is exponent. So never try to enter in calculators all those powers. Okay, which graph represents the relationship between strength and distance from point charge? The bigger the distance, the less electric field strength. Okay, so it's inverse relationship. If you have some point P between two parallel plates, positive on the top, negative on the bottom, so what will happen to that electron? So electron has negative charge. So electron will be moving towards two oppositely charged plate. So positive plate on the top. Okay, so it's here bigger. So negative charge will go towards to positive plate because it will be pushed away from negative plate on the bottom, right? So we are using the law of electrostatic charges. So opposite charges attract and the same charges will repel. Okay, moving electron is deflected by two oppositely charged parallel plates. What is direction of electric field between? Okay. Okay, because it's electron. Okay, so electron is moving between two plates. So if you remember from grade 11, we can use third right-hand rule for conventional current. But if it's electron, we are using a left-hand rule. And the same idea. So thumb represent your moving particle. So in grade 11, we were using current, but here just one electron. So left-hand rule. So thumb will show direction of electron. Okay, so force that will push that particle will have direction up. Okay. Region of influence surrounding an object is a field. So it could be gravitational field, it could be magnetic field, but usually we call field because it could be related to electrical charges, to gravitational. So this one is the best option you're selecting. Quantity remains the same between two parallel plates. Okay, potential energy changes because it depends from location. Electric potential also changes, and speed of the particle also doesn't stay the same. Okay, because when object particle is moving, it could speed up or slow down, so speed could change. So electric field between two parallel plates always will stay the same. Okay, in this diagram, point P is a point near a negatively charged particle. Okay, so negative charge. Which direction best represents the direction of electric field? Okay, because usually point charge is positive charge. So positive charge will be attracted to negative. So direction of the field will be to the left. Electric field strength between pair of parallel plates is E. Separation is double. Potential difference increased by factor of 4. What is the new electric field strength? Here is basically through writing equation what is strength and how strength relates to force and separation. And you get to E. Okay, so formula for electric field strength is voltage over distance. So if you decrease distance between two plates, so it's getting smaller, so denominator getting smaller, so electric field strength will get bigger. Or if you change potential difference on plates, also it will affect strength. But usually we keep the same potential difference, we change distance between plates, closer or further. So voltage on the plates and distance will affect electric field strength. So first formula is not correct. It's not even a formula related to energy. So current multiplied by resistance is not energy. Second one, force over charge. Okay, yeah, so it's not related to field strength. So voltage over distance. Two house points. Okay. Electron and a proton are in uniform electric field. What is the ratio of acceleration? So ratio of masses of protons to electrons gives you that ratio. And unit of electric field, okay, it's energy over charge. So energy we measure in joules and charge in coulombs. Okay, so whenever you have some unit analysis, try to think about using formulas. So if they mention about electric field, yeah, it's energy work done per charge. So it's not electric field is not equivalent to, oh, because of force, okay, electric field, voltage over distance. So voltage is volts per meter. So volts per meter is right. Force per charge. Yeah, force per charge is also unit for electric field. And energy divided by coulombs and divided by distance. Okay, yeah, so that one is not right. Okay, so basically you were doing very good. Only one student I resent to complete this quiz. Okay, I will go to Google Classroom to show you. Okay, show you what we will practice today. Okay, so what you see, some videos related to this chapter 7. So it's based on our textbook, Nelson, grade 12. So your teacher posted a link to Nelson textbook at the beginning of semester. So if you need to open it there, actually I can scroll through to remind, because somebody was asking me recently. It's like whole textbook online. Yeah, Creative Book Publisher. Okay, so if you forgot, you can go to, it's like, looks like October 1st or close to October 1st. So link creative textbooks. So it's big file, but it will take a few seconds to upload. Okay, actually I will go through. So it's chapter 7. So it's about electric charges and electric fields. Okay, so last time you were working with field lines, and today I want you to go over the rest of chapter 7. So Coulomb's law, electric potential, charged particles in electric field, Millikan experiment, how Millikan found the charge for electron, and to check how particles are moving in the electric field. And then you will need to check what happens in magnetic field to those particles. And we have also unit about light and matter-energy interface. Okay, so majority of ideas just to get some idea about those two units. Okay, so in chapter 7, just I will check through key ideas. Yes, easier to download this textbook and then to open on desktop because it a little bit freezes when you open online. Okay, so chapter 7 starts from page 290. So at the beginning, it's a review of grade 9 science when you work with charges and how to charge the object. So usually we are just quickly passing through this topic because you learned this in grade 9. So how to charge object, methods of charging by friction, by contact, by an induction, and only electrons could be moving. So protons and neutrons are inside of the atom in nucleus, they can't move. So application of electrostatics, photocopying machine. So you can look through technology that is used. Then for electric forces, okay, so you need to have idea what is Coulomb's law. So between charges, forces exist, and to calculate electrical force, you're using Coulomb's law formula. So force between 2 point charges is inversely proportional to the square of the distance between the charges. So it's in denominator r squared, distance between two charges, and directly proportional to the product of the two charges. So Q1, Q2, and K is proportionality coefficient known as Coulomb's constant. Okay, and this constant has unit 9 multiplied by 10 power 9 Newton multiplied by meter squared divided by Coulomb's squared. Example how to apply Coulomb's law. So if you have force between two small charges, so 5 multiplied by 10 power negative 9 newtons. How to get force if you increase distance 2 times and size and keep the same size of the charges. So distance will be twice bigger. So how it will affect forces? So usually we are thinking about coefficient of proportionality. So between force 1 and force 2. So force 1, it's initial force between two charges, and force 2, it's after you separated those charges on bigger distance, twice bigger. So ratio between forces is proportional to distance between them squared and inversely proportional. So you see that F2 over F1 equal R1 over R2 squared. So how to get force after you increase distance 2 times? You plug instead of are two coefficients that represent twice bigger distance. So R1 over R2, it's like 1/2. So you increase, so if you keep 1 as unit between two charges at the beginning, so after, distance is twice bigger. So R2 will be twice bigger. So what you will see, that force will be smaller, 4 times smaller, because when you put this coefficient in power 2, it will be 1/4. So you increase distance 2 times, force will be 4 times smaller. So you can play through forces, or you can think about coefficients. So how this coefficient between initial force and final force will be different. So distance will be twice bigger. So force will be 4 times smaller. Okay, and then what will happen if you change charges? Charge of one object is tripled, and charge of another one is halved. Okay, so 3 times bigger one charge, half smaller second charge. Also through coefficients. So now coefficient for charges. So second charge change and first charge change. So you put coefficient 1/2, so twice smaller, and 3 over 1, 3 times bigger. Okay, so force will not be 5 anymore, so it will be 7.5 multiplied by 10 power negative 5. So basically force will be bigger 1.5 times. Okay, so 3 over 2, 1/2. So 5 times 1/2, 7.5. Okay, so basically whenever you have questions about change of distance, change of charge, you need to work with coefficients. What is the magnitude of the force of repulsion between two small spheres? So you have distance between them 1 meter apart, and each charge is given. Okay, so you plug into Coulomb's law your coefficient, your two charges, and because they're both the same, you can put size of one charge and then in power 2, and distance between them squared, it's 1 meter squared. And you get force 9 multiplied by 10 power negative 15 newtons. So force is very small. Okay, so it's basically chug and plug into Coulomb's law, values for the charges and distance between charges squared. So always we use C units. So distance, if you have in centimeters, millimeters, you change into C system meters. And charge we measure in coulombs. So final answer, force will be in newtons. Okay, so whenever you have textbook questions, also try to check if you're getting the same answers when you're practicing such questions. Okay, so for charges along straight line, also try to think this way. You're dealing with charged particles, and force has magnitude and direction. So if you put some charge between another two charges, you need to think, what is the force, in which direction that force is moving? And we calculate forces between charges, for example, charge CA. So charge between those two, C and A, in which direction it will be. So to the right, because two positive charges will repel. So charge C will be pushed by charge A to the right. Okay, because the same charges will repel. C from B. So C from B will, okay, so charge B will push charge C to the left because opposites attract. Okay, and then try to think about two vectors, one vector to the right, one vector to the left. So how to get resultant vector? So bigger minus smaller and right direction of the larger vector. Okay, so larger vector was so larger, okay, to the right was 2.6 and to the left 1.4. Okay, so the bigger vector is to the right. So final solution will be also to the right. So bigger vector minus smaller vector, because when we add two vectors in opposite direction, it's basically subtraction. So 2.6 right minus 1.4 newtons to the right gives you 1.2 newtons to the right. okay, direction of the large vector. Okay, so if you have charges along straight line and you need to check what are forces on sphere C, always try to check how A and B affect this C. So A will push C to the right, B will attract charge C to the left. So you use Coulomb's law to find direction and magnitude of the columns from A on C, then from B on C, and you see that forces are in opposite direction, to the right and to the left. So find resultant by subtracting bigger minus smaller. And final force will be in direction of the larger force. Okay, again, Coulomb's law shows that force on charge is proportional to charges and inversely proportional to distance between them. Okay, so when objects are not along straight line, you need to apply basically the same idea. So how to get resultant vector? So in that example, you had along the square 4 charges. So 2 are positive. So those 2 charges are positive, 2 are negative. So you can look at combination on charge A. So charge A in that corner. How charge B will affect? Because they're opposite charges, it will be force of attraction. So force will be to the right of this charge. How another charges will affect? So check direction, magnitude, and find resultant force. Okay, and then basically for each charge, you get a resultant, and then find final force. And because it's a square, angles between hypotenuse and any side is 45 degrees. Okay, so force on the charge will be so many newtons and direction 45 degrees down from the right or east and south. But usually it's not applicable east nor south. So for charges, we just put to the left or to the right, up or down. Okay, so key idea, always check summary for each chapter. So how to get force of force at X on the charges. So using Coulomb's law formula. And what is similar, what is different between gravitational forces and electrical forces. So in denominator for both forces, you have distance between objects squared. So in gravitational forces, objects are big bodies, and for charges, it's distance between charges. Forces act along line joining two centers of masses or charges. Okay, so the difference, gravitational force can only attract, so always attractive forces. So there is no repulsion. But for electrical forces, the same charges will repel. So both positive will repel or both negative will repel. Okay, and size. So universal gravitational constant, it's a capital G, is very small. But Coulomb's constant is very large. It's like 9 multiplied by 10 in power 9. Okay, so huge K, but very small G for universal gravitation. Okay, for about electric fields. Okay, so between regions in space, a field of force exists. Okay, for gravitational field lines, out of north towards south. So Earth is a huge magnet. Okay, for electrical forces, like what you did last time, so out of positive towards negative electrical field lines. And electrical field lines is a ratio between force to charge for separate object, like not between plates. So separate charges, force over charge. And units, so newtons per coulomb. We can use for separate charges, force for Coulomb's law. So K multiplied by product of two charges divided by distance between them. And then when you simplify, so Q on the top and Q on the bottom will be cancelled. And what you'll see, electric field is proportional to charge and inversely proportional to distance squared. Okay, so for separate charge. Okay, and here field lines, how to draw them. So if charges have the same strength, so you have like symmetrical lines, but if they're not the same size, like bigger, so you will not have like really symmetrical. Okay. But still you have lots of curves. And again, density is close to the charge. Between parallel plates, you have uniform field between. Only in the corner, it's not uniform. So age effect. So it's negligible in the fundamental theory of parallel plates, produces a weak field, shown here with field lines far apart at the edge of the plates. Okay, so how to create? You connect some power source, battery, and you charge one plate positive, another plate negative. So examples how to calculate electric field. So charge over distance squared. So coefficient K is always constant. It's a huge number, 9 multiplied by 10 to the power 9. So if you have charges on some distance, how to calculate electric field? So you substitute charge, coefficient, and distance between two charges. And distance should be in meters in the system. Okay, application of electric fields, electrostatic precipitators. So they clean the air, so it's good for environment. So they remove particles from the gases in large industrial facilities. Okay, so summary for 7.3. So what is electric field? Where it exists, so in region of space where you have some charges. How to calculate force over charge, and it's electric field for any point. Electric potential. Okay, so you're familiar with electric potential energy. So for mechanical energy, it was energy that was related to position of the object and mass of the object, so mgh. For electrical field, it's something similar. So it's energy stored in a system of two charges, a distance r apart. So if you divide force, okay, if you multiply force by charge, force by distance. Okay, so what is energy? So energy is work done. So work is force multiplied by displacement to distance. So if you multiply electrical force from Coulomb's law by distance r, so r squared will disappear, it will be only r. Okay, so force multiplied by distance gives you work done or energy. So potential energy is the product of two charges divided by distance, so not squared anymore, and multiplied by some coefficient, proportionality. That is very big. So 9 multiplied by 10 to the power 9. Okay, so this distance, potential energy decreases. Okay, and we call electric potential, it's electrical energy per charge. So electrical energy is like force multiplied by displacement, like that formula. So K, product of two charges divided by distance, divided by charge. And when we simplify, so charge on the top and charge on the bottom, we have formula for electric potential. So product of coefficient and charge divided by distance. Okay, so units, 1 volts. So we call it electric potential at a point in electric field of 1 joule of work. required to move one coulomb of charge from infinity to that point. Okay, so 1 volts, it's 1 joule per coulomb. Okay, so when object move between plates, it loses or gains some energy, and potential energy we count as charge multiplied by delta V. So delta V is that voltage energy that changes moving from one place to another. Okay, and again, we can relate. So what is electric field strength is force over charge. When object is moving from one place to another, force changes, and we can count potential difference as voltage over distance. Okay. So an example, so how to get electric potential of a distance, so 40 centimeters between plates, or from spherical point of charge of so many coulombs. Okay, so you have distance from charge, so you have how big is this charge, and how to get voltage, so K multiplied by charge divided by distance between plates. So voltage will be so big, so many volts. How much work was done to move some charge between plates, so by 120 volts. Okay, so work done is energy, change of energy, and it's electrical energy. So it's charge multiplied by voltage. So charge is given, voltage is 120 volts, so you multiply them and you have work done by plates. Okay, in uniform electric field, potential difference between 2 points is 12 centimeters. So we change in meters right away, so divide by 100. And voltage is given. Find the magnitude of electric field strength. So it's voltage over distance. Okay, and strength we measure in force over charge, like newtons per coulomb. Okay, so how to get magnitude of electric field strength between two parallel plates? Okay, magnitude of electric field strength between two parallel plates is 450 newtons per coulombs. Okay, you connect them to the battery with potential difference 95 volts. What is the plate separation? So distance between plates you need to get. Okay, so it's uniform electric field. So you have strength, you have voltage, how to get distance. So electric field strength is proportional to voltage and divided by distance. We rearrange in terms of distance, and it's voltage over strength. So 21 centimeter is distance between those two plates. Okay, so just to get idea, so that for charge is different formulas than for plates. Okay. Okay, so summary for electric potential. So if you have two charges, electric potential difference between them equal, like force multiplied by displacement, try to think this way, and Coulomb's formula for Coulomb's law multiplied by distance will make square disappear. So product of two charges multiplied by coefficient divided by distance is electric potential energy between two charges. How to get voltage? You divide energy by you multiply. Yeah, you multiply by okay, so energy, so potential is energy per charge. So you divide by one of the charges, and charge will disappear from formula for energy. So potential equal energy over charge. So K multiplied by one charge divided by distance. Yeah, it's basically, it should be earlier. So energy over charge gives you formula for voltage. And a magnitude, so electric field strength is basically the change of potential difference over distance or radius, how far it's located. Okay, so Millikan experiment. Okay, so what Millikan did, so he was measuring motion of charged particle in electrical field. And his huge discovery was that he found the charge for elementary particle, and it was charge for electron. So he was putting charge between two charged plates and was making balanced motion. So force of gravity and electrical force, he was trying to stabilize and to see how it will affect the motion of particle. So electrical force is proportional to charge and electric field strength, and force of gravity that acts on this particle down is mg. So electrical force is equal to force of gravity. So he was spending like so much time to balance, to find what is the perfect condition, so to make it happen. And he found that every time it's discrete portions of particles are moving, and he started to find the elementary particles, and he found the charge for one electron. So he got a Nobel Prize for this. So it was like a huge discovery. So amount of charges in one particles was proportional to number of electrons, and he found that it's discrete amount every time. So he found a charge of one electron. And here just example, so how we can apply it. So if you have so many electrons and you need to find charge of small sphere. So Q is charge of small sphere. It's number of electrons multiplied by charge of one electron gives you such big charge. Okay, for Millikan experiment, what you need to know, like free body diagram, so which forces act on the object. So he had particle balanced between two plates. Okay, so if you have positive plate on the bottom and negative on the top, to balance the particle, so you need to have positive charge. So positive will be pushed away from positive, right? And will be attracted to negative. So this way, so particle is stabilized, it's at rest or moves with constant speed. Okay, so no acceleration. Because if object will have unbalanced forces, it will start moving with acceleration and forces will be not balanced. Okay, so he wanted to have a balance. So if you will change particle, if for example you have negatively charged particle, so you need to reverse charge on the plates. Okay. Okay, so summary. So Millikan was able to find charge of one electron, and it's 1.6 multiplied by 10 power negative 19 coulombs. Okay, so classical questions. It's like question number 3. Okay, so you're putting between plates some charge, you have distance between plates, you have potential difference. So you will be able to find charge of oil drop, number of elementary particles, and then to check if you have extra electrons or lack of electrons. Okay, if charge is moving, it has kinetic energy, and electrical energy is product of charge and voltage. So we can use this principle also to find what is the speed of the particle inside of the field. So how to get speed? You divide both sides by 1/2 m and take square root. So basically to get speed of the particles inside of cathode tube, you multiply charge by potential difference, divide by mass of the particle, and because it's positively charged, so mass of the electron, and mass of the electron is constant. Okay, so 9.1 multiplied by 10 pound negative 61 kilogram. So you will be able to find with which speed that electron is moving. Okay, and when electron is moving between plates, you will be able to use your hand to find direction and force on particle between plates. Okay, and summary. So when particle is in an electrical field, charged particle will be in uniform electric field. So it's between two plates, it's uniform field, and acceleration will be constant. So acceleration constant, so it means speed will increase by constant rate. And we can change kinetic energy to electric from corresponding changes of electric potential energy. Okay, so at the end of the chapter, you have a key idea, key expectation, and concepts. So try to go through key equations. So how to find force between charges. So it's formula that represents Coulomb's law. So what is coefficient for Coulomb's law? So it's very big. So for gravitational forces, K is very small. So, and for gravitational, it's really G. So G is very small. Okay, then you have, discovery of Millikan. So he found charge for electron and how to get total charge, number of charges multiplied by charge of one electron. Okay, so you can look through cell case. I will upload also question on quizzes, so you can try some conceptual questions and some calculations on Millikan experiment. So it will take maybe in 10-15 minutes. Okay, so I wanted to go through chapter 7 and on chapter 7 videos. So try to look through videos uploaded on your Google Classroom. Okay, again, it's first link here. Okay, so properties of electric charge, Coulomb's law, electric fields, electric potential, energy and potential difference, and electric potential due to point charge, and Millikan oil drop experiment. Okay, so for Millikan oil drop experiment, very important to write which forces are acting on the object, because most of the time you just need to rearrange left and right side of that equation to find maybe distance, maybe speed. Okay. So 10 minutes, 10-15 minutes till, okay, now it's 10:06. Okay, till 2:20. So go over videos and worksheets. Okay, yeah, here, chapter 7 notes field. So actually it has some examples how to solve problems. Okay, so try to go, okay, till 2:30. Okay, go over file, this file and videos. Okay, so I will put note on the chat. Okay, go over uploaded files. Okay, so I will upload some quiz on quizzes. So I will assign. Yeah. Okay, so keep working. Okay, so it's close to 2:30. Okay, so try to wrap up your reading, and I posted on Google Classroom some work that you can check. It's 11 questions multiple choice on forces. Yeah, so in a couple minutes at 2:30, you can think about those questions, and we can do like short discussion maybe. Yeah, Levin, yes, sir. I hear. Okay, let's go through questions. Like at first, like discussion. What do you think is important for each question? Why? In which direction of forces? Which one is bigger? Which one is smaller? Yeah, Levin, yes, sir. I hear. Okay, I see somebody responded. Okay, yes, it is here. Okay, Lorraine is here. Okay, good, good. Uh, so you prefer to chat, not to talk. Can you unhide your microphone? It's more complicated to type. Like you can unhide and you can talk. Like for the first question, like I want to hear, like, what do you think we should select and why? So they're talking about two exoplanets in orbit. They exert a gravitational force on each other, which diagram shows the magnitude and direction of the forces involved. Okay, so gravitational forces between two planets. So in which direction they are? Are they different in size? Are the same in size? So what do you think? So which option do you think is there? A, B, C, or D, and why? Try to think which one doesn't belong at first. Okay, so if you know about gravitational forces, they act between object, and the gravitational forces are always attracted forces, like forces of attraction, no repulsion. So which picture shows repulsion forces? Which one you can exclude right away? So you can type your question. So if you prefer not to talk, okay, can you write? Okay, you can type. Which one is out? Which option? So which one doesn't belong? Which one doesn't belong? It's like easy way how to cancel which questions right away don't fit. So you need to find a diagram that correctly shows magnitude and direction of the forces involved. So right away, this one doesn't belong because here forces are towards to the planet and gravitational forces are attracted forces only towards to the planet. So right away is not there. What you can see about first one. So gravitational forces are proportional to,
Is the answer C?
yep, and why?
Because it's both pointing at each other, so it's attracting each other.
Yeah, but A and B are also attracted. So why?
But they're attracted in the same level. Like, so A and B, it's not the same. It's like different length.
And what do you see from A and B? So look at the size of those planets and vector. Like how to relate these two concepts, like how to calculate force of gravity. Do you remember the formula? Like today we were mentioning that all those forces, magnetic, gravitational, electric, they are similar. You have some coefficient, then you have product of two objects, like charges or masses. So here you have small mass and bigger mass. We can use smaller letter and bigger one. And what is in denominator? So for all of them, it's something similar. Distance between them squared. So it's distance between square mass, radius is like this between centers of mass. So what we see on all those pictures, so denominator is the same, right? masses are different, but if you have bigger mass and smaller force and bigger vector, bigger force, it's not applicable. So forces are equal and opposite. So here it's only C. Okay, next one is B, second one, 3 masses. Okay, so Lorraine, you're right. ABC gravitationally attract one another, between which pair is the force the greatest. So object A, 3 masses. Object B is like 1 unit of mass, and object C is the biggest one, 12 masses. And distance, you see, R, and here twice bigger distance. Okay. So between which pair is the force is the biggest one. So between AB, okay, those objects, or between BC, or between AC, or they're all equal. So which one doesn't belong right away?
A and B doesn't belong.
Okay, A and B doesn't belong, and why? Like, why do you think they don't belong? So if you calculate,
Because it's asking for the greatest, and
Mhm.
A and B is the shortest.
And how to calculate force between AB, for example, force between AB. So coefficient will be the same, G. Okay, but when you plug, okay, so coefficient and product of 2 masses. So 2 masses for AB is 3m and m, right? So 3m multiplied by m. And distance between them will be r squared. Now compare this force between BC. Okay, so what we should write in numerator? So between BC, so mass of B is m. Mass of C is how big? 12m. And distance between them squared. So 2r squared gives you 4r squared. Okay, so when we reduce 12 divided by 4 is 3. Okay, so those forces are equal to each other, and force between AC okay, what should I write? G, okay, what should be on the top between A and C? Which are 2 masses are there? 3m and 12m. And distance between them. R plus 2r gives you 3r and everything squared, so it's 9r squared. Okay, so 3 multiplied by 12. 36, 36 divided by 9, 4. So force will be 4 times F. Here it will be 3F. And here it will be 3F. Okay, so force between AB equal force between BC, 3F. But force between A and C is bigger, is 4 times F. Okay, that's why it's AC. Bigger force, 4 times from original force. Okay, so always you need to be able to justify by using formulas. Okay, number 3. Okay, electric field at a point on a line between 2 charges Q1 and Q2 is 0. What can you conclude about the sign of two charges? Okay, so number 3, okay, think.
Would it be opposite sign?
Okay, so Q1 opposite, like what is positive, one is negative. Try to think like what is electric field? Electric field, it's vector. Okay, and we want to have it 0, right? So what about charges between Q1 and Q2? Okay,
So it would be the same sign.
same sign here. So it will be A, the same sign.
Yeah.
Okay, both positive or both negative. Okay. Okay, number 4, the field for unknown object is known. What type of field could this diagram represent? Okay, so out of. So field lines are going out.
Would it be electric?
Yeah, it's electric, and it looks like charge inside is which side? So if lines are going out, so if you have positive and negative, so out of positive, but towards negative, right? So here it looks like positive charge, electric. Because for gravitational, always attractive, always towards to it. Magnetic, it's not always like that. North and south you have. So you can have out of doors towards south, but here it looks like electric charge. Number 5, on average day, the electric field of the Earth's atmosphere is directly downward. What is the charge of Earth? Okay, electric field is down. So here is Earth. Yeah, towards to Earth charges. Okay, when is towards to Earth? So electric field line are going towards if it's negative.
So it would be positive.
No, negative.
Negative?
If it's
But
positive,
isn't it if it's going to the earth?
but they're saying directed downwards. So downwards towards to Earth. And electric field lines are going towards to negative, out of positive. Okay, so Earth will have negative charge. So directed down to negative. Okay, number 6. So you have 2 equations for electric field. What's the difference between them? Okay, think about this force. So it's Coulomb's force between charges. And Coulomb's force is coefficient, product of 2 charges, divided by distance between them squared. Right, and energy, it's force divided by charge. So one of the charges will disappear, see, divided. So one will be gone, and you're getting exactly the same formula, right? So you're getting exactly the same formula. So it means they are all correct. So first describe producer, second experiencer. Yeah, it's like they are related. You are getting one formula through another. Okay, so force over charge. And here when you will substitute charge divided by distance squared and put units for coefficient K, also it will be force over charge, newtons per coulomb. It's analogy to gravitational force strength. Okay, for gravitational field strength, G, what is G? It's force over, it's like force of gravity equal mg. So what is G? Force over mass. So in our case, coefficient, gravitational coefficient, it's also force over unit charge. Okay, so everything is correct here. Okay, number 7. Which of the following electric field diagrams are incorrect? Okay, so you need to think direction. So out of positive towards to negative. Okay, which one is correct? Which one is not?
So are we supposed to do like the positives or the negatives?
So out of positive towards to negative, which one incorrect? Circle all that apply. So everything could be, or maybe only one. So you see all that apply.
So we have to cancel out A
Why?
because it doesn't fit the need. It's not correct.
Oh, just 1 second. Somebody wrote. Yasser wrote. Oh, Yasser was writing here on the typing. He just. So he wrote right now, B is wrong. Okay, and Yasser, can you explain why B is wrong? Okay, explain why. Okay, so he wrote it's a negative charge, but the point out when it's pointing in. Okay, so here is out, here it's in. Yeah, so this one doesn't work. Here is out, but
Is C also, I mean D, my bad. Is D also wrong?
yeah, it's also wrong because it should be out of positive towards negative. So okay, to positive will repel. Okay, looks good. Okay, so incorrect looks like that one. Yeah, and that one. And this one, it looks like if it will be stronger charge. Okay, it could work. Okay, let's check number 8. You have parallel plates. Okay, so remember in parallel plates, you have uniform field between. So atom positive moves from 1 to 2. Okay, potential energy, positive, negative, or 0, when atom moves from 1 to 2. So situation A, like first word, and situation B, second word. Okay, so yes, wrote it's a negative charge, but it points out when it should be pointing in. Okay, so you're thinking about field lines, not about potential energy. Potential energy increases or decreases. Try to think the same way, like similar as mechanical energy, if height will change. So it's not positive, negative. Okay, so no yes, sir. In second picture, so you're moving from one position to another. So height doesn't change, basically. Try to think about height of the distance. So it's not moving closer to any of them. So here it's 0. Okay, and here it's positive particle, so positive ion, and it moves to negative plate. Okay, so positive will be attracted to negative. Okay, electric potential energy will be negative. So negative. Okay, so moves towards to negative. So potential energy will be negative. Okay, what would be electrical energy for neutral atom in diagram 1 above? Okay, so charge is 0. So it's moving between plates on first picture. Okay, so you think that if charge is positive and negative, it's affected by electrical field. But if charge is 0, so neutral object not affected by electrical field. Okay, so it will be 0. Okay. Okay. So for number 9, it's negative charge, but it's point out when it should be pointing in. Okay. Okay. So, okay. Yeah, I'm checking like previous one. Okay. So 0 charge, not affected. So it's 0. Okay. Number 10. Suppose you look directly from south pole to bar magnet, magnetic field points to the right, to the left, away, towards. Okay, down from south pole on bar magnet.
I'm sorry, but what was the answer for question 9?
9 is 0 because it's not
0.
object. Yeah, so it's not affected by electrical field. Only positive, negative charge is affected. Okay, so I'm trying to say like, how they located that magnet. You look directly down on south pole.
Wait, my bad. I made a mistake. I meant for question 8.
Or 8, 8, let's say negative and 0, so it's C, the recommend to answer. So negative potential energy, and here 0. So C. Okay, you look directly down on south pole, so it looks like you're looking here and here north. So magnetic field point. Okay, magnetic field lines out of north towards south. Okay, so how they're trying to say away from you. Okay, so maybe they want to see like this way. Okay, so magnetic field lines
It
out of north
could be
away from,
towards.
they recommend to answer like away from you. So it looks like away from you towards south. Yeah. and magnetic field lines are close to the ends, high density. So inter, and you're looking to that end, south end. Okay, and let's check last one. Suppose you wanted to deflect a positive charge in south pass as shown, using only magnetic fields. How could this be done using magnetic fields perpendicular to the plane of the page? How does velocity compare to velocity out, velocity in? Okay, positive particle, so it's right-hand rule. Magnetic field perpendicular to the plane of the page. Okay, so B is magnetic field lines, so perpendicular to the plane. So we can show perpendicular, so it's into the page. So vector B. Out this velocity increases. It doesn't matter if velocity increases or not. And they don't say that it's answer B. Okay, so try to think other way. So try to use right-hand rule. So you have positive particle, right hand. So your thumb will show direction of your particle. B is into the page. Okay, and they're asking about velocity out compared to velocity in. Okay, velocity out, velocity in. Okay, velocity doesn't change. Okay, what happens here? Force is up. That's why it's circling into the page. Okay, so if you put your thumb this direction, okay, thumb direction to the right, and your fingers 1, 2, 3, 4. It's your magnetic field lines. So your force is up. That's why. Okay, so here velocity. Here 4 fingers into the page. So force will go that way towards. Now it changes. Again changes. B stays the same. Okay, so velocity doesn't change, and be in and then be out of the page. Okay, because it changes direction, it means be here will be into the page. Circling. Okay, so it's magnetic field lines will change direction, so object will change path. Okay. Okay, it's 3 o'clock, time to finish. Okay, just wrap up. Any questions on that quiz? It's basic concepts. Okay, gravitational, magnetic, and electrical fields. So they're all related. Distance increases, so forces increases. Force gets smaller. Sorry. So a distance between object in gravitational field or electrical field. So distance gets bigger, force gets smaller.